All right, everyone, in this next video, we're going to practice how to match signals to a structure. Now, this is a really common problem type. You should expect to see this on your exam. Be prepared for this. Now, when we approach a problem type like this, what we're going to want to do is first use chemical shift as a filtering factor, and then if need be, we can also use splitting pattern to our advantage. So what I mean by chemical shift is this. We could say that, this is our aryl region, 6.5 to 8 approximately. Those would be our protons on our benzene ring, meaning they're going to represent C, B, and A. From there, what I might do is say, okay, those are all aryl. Well, let me look at the split pattern, singlet, doublet, and doublet. These two peaks here are the ones indicated for that signal. Now, right away, I can say that C is a singlet, so the singlet is C, but A and B are both split into a doublet. So now what I'm going to have to do is go back to chemical shift, and there's going to be a nuance in chemical shift distinguishing these two. What I'm going to acknowledge is that the oxygen is attached to the benzene ring, and that's a resonance donating group. Now, because it's resonance donating, what I need to annotate is that it's going to create negativity, ortho to it, and para to it. This is what we talked about earlier. The donating group causes negativity to be ortho and para relative to it. Then the C double bond O is a resonance withdrawing group. As it withdraws out of the ring, it would put positivity, ortho, and para to it. Now you'll notice that at position B, it's receiving that positivity, whereas A is receiving the negativity. If B is receiving that positivity, that means it's extra D-shielded. Because A is receiving the negativity, that means it's extra shielded. And given that analysis, I would say here we could distinguish that B is the more downfield aryl signal, that's a doublet, and A is some more upfield shifting doublet aryl signal. So just be careful on the benzene ring. We don't want to assume that it's because it's closer to the oxygen, it's more de-shielded. We can't forget that the oxygen has resonance donation with the benzene ring and therefore creates negativity, ortho, and para, and thus A is more shielded comparatively. That's very important to do. And on the exam, after you label A, B, and C, you might just cross those out to say, I've already used those, to just be able to quickly distinguish which protons are left. I'm then going to look at the next most downfield signal, and if I haven't stated this already, when we look at chemical shift and we're trying to relate signals, you want to read from downfield to upfield. We read downfield to upfield to distinguish signals. The next signal is fairly far downfield. It's a quartet, and I would say that would correspond to G. That's a proton on a carbon bonded to oxygen, which would be in that 3 to 5 region. So that's G, quartet. Then we have another quartet, which is a bit more upfield compared to G, and that would be D. That's a proton on a carbon neighboring a pi system, and you'll notice that D is split into a quartet by proton type HF. Then I see a doublet, and that's different in splitting pattern from the remainder. So I could just use splitting pattern alone to identify that that doublet is E. E is split into a doublet by the one hydrogen adjacent to it. Then between the two triplets, I'm going to have to look at a subtlety in chemical shift. It's going to represent either F and H. And I would say that H is closer to a more prominent inductive effect than F is, because we've stated before that proton on a carbon is 3 to 5. Proton on a carbon bonded to pi system is going to be 1.5 to 2.5. Now, H and F are both technically protons on a carbon adjacent to another sp3 atom. But how they're different is H is then next to an oxygen, and F is next adjacent to a pi system. So given that info, I'd say H is more downfield than F because H is closer to a more prominent inductive effect compared to F. Okay. So as we solve, we want to use chemical shift to our advantage. You might start with the aryl protons. We have the aryl region. We use splitting to distinguish them. And if two have the same splitting, there's probably some subtlety in chemical shift. From there, we go to the next most downfield signal. And you can scan for the next most downfield proton type. We can use splitting pattern also to aid us in that. And especially with the more upfield signals, that's where we might have to use chemical shift again if the splitting pattern is the same. But for this signal here, that was a doublet, and the rest were not doublets, so it's pretty easy to distinguish E from the rest of those. We're now going to do this again here. So I'm going to scan my structure really quickly, then I look at my spectrum. What I'm seeing is I've got a broad singlet here around 16 point something. I've also got another broad singlet here, so that will represent G and F. Now, of the two, I would say F is the more downfield shifting signal, G is the more upfield shifting signal. Usually carboxyl protons are around 12 and phenolic OH protons are around 9. It appears that in this example they're a little bit more downfield shifting, but nevertheless we could say that F, carboxyl proton, should be more downfield than the phenolic OH. From there we have 6.5 to 8, which will be the aryl region. Those would be the protons on the benzene ring. And honestly, this comparison is a really tough comparison. So on the exam, they might just have you label those together. Okay, just, in one box and say, oh, A and B. The answer here is that B is the more downfield shifting one and A is the more upfield shifting one. Acknowledging that the OH is resonance donating, we'd put negativity at the ortho and para positions. Then the C double bond O is a withdrawing group that would put positivity at its ortho and para positions. So why this is a difficult comparison, and just notice A and B are both getting the negative and the positive. The way that I'd rationalize why A is more upfield shifting here is when the oxygen is resonance donating in, A is receiving the negativity and kind of the brunt, so to speak, the more intense flow from the resonance donation. And so the ortho position there might be a little bit more shielded compared to the para. And therefore, A is the more upfield of the two. But on the exam, they might just have you put one box and put A/B, because that is a difficult comparison to make, honestly. Moving on to the next most downfield signal, that appears to be a quartet. So I'd look for something that's deshielded and a quartet pattern. That appears to be C split into a quartet by the protons at position E. Then I've got this really complex split signal, and it might be tough to tell exactly if it's a septet or sextet. Let's just say it's a multiplet. But what we know for sure is that that proton set is receiving splitting from multiple directions. And I would say that's proton type HD, because it's split by the two methyl sets here. Okay, complexly split. Then it looks like I've got a triplet and a doublet. The triplet is going to be E, split by the two hydrogens at position C. And the doublet would be proton HH, split by the one hydrogen here. All right, so they're kind of easier to distinguish the more upfield ones. Big takeaway from this, carboxyl proton should be more downfield compared to phenolic OHs. Okay, and remember those two chemical shifts were fairly predictable because we had sp2 oxygens. If you had an alcohol just having an sp3 oxygen, chemical shift is a lot more variable, 2 to 7, and that's also where you'd see sp3 nitrogens bonded to protons as well. There's an overlap there. Moving on to the next example. We have a broad singlet here around 12. We also have another broad singlet here around close to 9, give or take. So that would represent B versus C. I would say that the carboxyl group ought to be the more downfield shifting signal, closer to 12, and B is the more upfield shifting signal. Pausing for a second, in an earlier video, I stated that if the splitting pattern was the same, assuming the splitting pattern is the same, that's very important. Assuming splitting pattern is the same, you could use the height of the peak as a metric for the number of protons. So because these are both broad singlets, and this one's taller, that one should be associated with more protons. Because this is a broad singlet and so is that, and this is smaller, it should be associated with less protons. But again, you can't compare like a singlet height to like a triplet height. We cannot compare if splitting pattern is different in that way. Cannot compare the heights if the splitting pattern is different. Okay. All right, then I have a triplet here and another triplet. Now, D would be a triplet split by those two adjacent hydrogens, and A is also a triplet split by those two hydrogens. So we have to use chemical shift to distinguish these. I'm going to say that D is the more downfield shifting proton of the two, because D is experiencing withdrawal from the C double bond O and withdrawal from the nitrogen. A is only experiencing withdrawal from the sulfur, and remember, sulfur is not that much more electronegative than carbon. So it's a more mild withdrawal compared to even just the effect of the nitrogen. In other words, proton on a carbon simply bonded to nitrogen should be more downfield than proton on a carbon bonded to sulfur. And I would say definitely, as we see in this example, proton on a carbon bonded to nitrogen and a pi system would be more downfield than proton on a carbon bonded to sulfur. Okay. Now notice that sometimes you won't see certain positions labeled. They're probably doing that for a reason, like the proton set here and here. are actually kind of overlapping, and so they didn't make us distinguish it in this example, okay? And in other examples, you might have, a bunch of labels, A, B, C, D, E, F, G, and there might be fewer boxes than there are protons. So there's a chance that you might not use all of them, just to throw that out there. All right, looking at this next example, number 4, scanning our structure. Okay, cool. We're seeing that the most downfield signal is a broad singlet. So it has to be an OH or an NH, and the only one that's an OH/NH would be proton type E, phenolic OH, kind of by 9. Then we have our aryl region, protons on the benzene ring, and that would represent C versus F. Notice that both of those are singlets, so I have to use a subtlety in chemical shift. Now, you'll also notice that the nitrogen is within the ring. If the nitrogen is within the ring, it actually has an inductive effect, so it's kind of pulling electrons towards it. I would say that's enough right there to say that C is more downfield than F. Nitrogen is pulling more predominantly from C. Now, for argument's sake, let's say that nitrogen wasn't there. If it wasn't there, then I would have to acknowledge the OH is on the ring, and that would resonance donate. And that would put negativity at the ortho and the pair positions. So again, assuming that the nitrogen isn't there, notice that C receives the negativity, but F does not, and therefore C would be more upfield if the nitrogen wasn't there. But because the nitrogen is there, the nitrogen has an inductive effect from C, which is felt more strongly because it's closer to the nitrogen than F is. Okay? The next most downfield signal is a singlet. I'm going to say that's I, because that's a proton on a carbon bonded to oxygen, receiving an inductive effect there, and an inductive effect from the benzene ring. And it's a singlet. Looking at the next most downfield signal, it's a quartet. And as I scan my structure, I might be noticing, protons adjacent to the pi systems, because that's the next most withdrawing effect present. But D would be split into a triplet, and G would be split into a quartet by the adjacent methyl group. So this signal here represents G, split into a quartet. The next most downfield signal is a triplet. I would say that's D. Okay, that would be D. And both of these types of protons here, let's make a note, are protons on a carbon neighboring a pi system. And notice that G is a little bit more downfield. I would say that's probably because G is experiencing some effect from that nitrogen within the ring. Okay, but without that inductive effect, we could use splitting pattern to distinguish G and D. All right, then we've got a very complex signal here. And if you zoomed in, you would see that that's a sextet indicating the presence of 5 neighbors. Of the remaining protons, it is proton type HH. That would actually be complexly split. And in theory, it's split into a triplet of quartets, but you'll notice that it's appearing as a sextet, where in the spectrum is just giving you n plus 1, whereas in theory, its splitting pattern would be n plus 1 times n plus 1, triplet of quartets, which is appearing in the spectrum as that sextet. From there, we have a triplet and a triplet, the two most upfield signals. We have to differentiate B versus A. I would say that A is likely to be more downfield, higher chemical shift, given that it's more proximal, closer to inductive effects. B is further away from inductive effects than A. So B is the most upfield shifting proton type. Okay. So I can't stress this enough. These problem types are very, very important for you to have down. If you want to use chemical shift as your first filtering factor, I recommend reading downfield to upfield. We then use chemical shift if need be to differentiate signals. And if you've already used chemical shift and splitting, as we did to distinguish A and B here, there's maybe a subtlety with chemical shift to further distinguish. Okay, we read downfield to upfield, and you'll notice that I kind of labeled the splitting pattern of each peak as I got into the spectrum. You don't have to go across right away and label all of them. I would label the splitting pattern once you get to the analysis of a given peak. And as you're, doing these questions, you can even think about your chemical shift regions. Here's that chart again. You can use that chart as you're solving those problems. Okay. Got to be able to solve these types of questions, matching signals.